Hey, what's up, guys? Chung here again. And so today, let's take a look at LeetCode problem 1548, the most similar path in the graph. It's a hard problem. I think it deserves an upvote. Okay, so you have n cities and m bidirectional roads. So basically, from the first sentence, you can already find out. See, this is a graph problem, right? Basically, you have n cities and m edges between those n cities, and each city has a name, consists of exactly three uppercase English letters, whatever. Basically, each city has a name, and the name stores in a names array here. And starting at any city X, you can reach any city Y, where okay, and then you'll be given like a string array target path. You should find a path in the graph of the same length and with the minimum added distance to target the path. Okay, so what's what's the added distance? Okay, so it defines the added distance as follows here. Basically, it just the added distance is like the how many different names do we have in our path comparing with the target path. That's the added distance. Okay. Uh, yeah, and and then you need to return the order of the nodes in the path with the minimum added distance. We'll talk about follow-up later on. So basically, for example, there's like this like a example here. There are like n nodes and like 6 rows, right? Because for 5 nodes, for n nodes there's n plus 1 edges, right? And the name for each node is follows, and there's a target path. So the length of target path it's not fixed. It could be 4. In this case, it's 4. It could be 5. It could be 10. Right? Doesn't really matter. So and it asks you to find the output. The actually sorry, the output is a path. Not only the smallest added distance, but it also asks you to find the path. Okay. So in this case, so 0242 is one of the answers. Remember, so there could be multiple answers, and you can just return any of them because so the target path is Atlanta, is it ATL? I don't know, what's this, Dallas? Maybe DXB, HDN, and LAX. And if we go to from 0242, then we have ATL, DXB, uh, sorry, we have ALT, yeah, here, LAX, HND, and LAX, and the added distance with the target path is only one, which is only the only difference is this one, LAX. Okay, here's some other examples here. Yeah, same thing here. Okay, so that's some numbers estimation here. And the graph is guaranteed to be connected, and each pair of nodes may have at most one direction node. Yeah, and yeah, there can be 2 cities with the same name. Okay, yeah, cool. So basically, I know it's a long description, but it's a good problem. Basically, you guys can see it's already a graph problem. But what makes this problem a hard problem is that on top of the graph problem, there's also like a DP concept on top of it. So, um, because here we have a target, right? And we don't know what's the basically we have to try all the possible paths here. And from all the possible paths here, we have to find a path, right, that has the minimum target length. And even if we find that, and besides finding that minimum added distance, we also need to somehow like uh, save the path so that we can reconstruct the path after we traversing all the nodes here. So I think so first thing we need to define is a DP here. Okay, and so I'm going to define the DP here, the DP I and j, right? So that's the state transition function. Okay, so what does dpij means? Dpij in my case it means that we have already traveled ith city. Okay, basically from zero from zero to I, from zero to I, and the last city. Last city is J. Yeah, of course this is J is like the index of the cities here. Okay, so that's my DP. Okay, so what's gonna be the value of that, right? So and I think here it's not that hard to find out, right? So basically from dpij, how many ways we can get to the dpij, right? Basically there could, so it's gonna be the minimum, right? The minimum of dp uh, I plus uh, actually I'm gonna use the v here because in the graph we usually for edge, right? For the edge in the graph we always use a u and a v. Okay, u and v to represent the graph. So here I'm using the v here, and so it's going to be the minimum, sorry, the I minus 1, right? From the last step, which is the I minus 1, and but from which node, right? So we're going to have the u, okay? So let's say, for example, we are at the PEK here. I think it's the Peking somewhere. So I think it's PEK here. And how many ways we can get to the PEK here? There are three nodes, right? From DXB, from LAX, and from HDM. Okay, because there are three edge, right? Basically, this U will be like from three of them, and plus what? Plus the current added distance. Since we have the i's here, right? We have the I here, and we know the PEK here, and since we have the what the index of our current position, we can also find what's the expecting cities in the target path. Okay, and then this one could be either 0, 1 or 0, right? This thing depends on the our current cities at ith position if it matches with the target path. If it doesn't, if it matches, then we know okay, this is something matches. Then we know okay, there's no distance. If it doesn't match, then we know okay, we need to add 1. And we do this, right? We do this for all the DPI minus 1 that have an edge uh, to our current city here, and we'll find the minimum one. Okay, so that's that. I mean, if we're only asked to find the minimum path, then it's not that hard, right? We just keep like uh doing this, and in the end, so we have a DP I think n, right? I think DP n here, n minus 1, yeah, n minus 1, and we just find the max, sorry, the minimum of the DP n minus 1 because for all the cities here. That's how we get the minimum value. Okay. But this problem not only it needs us to find the minimum added distance, it also asks to print the path. Okay, so add, that's what adds like another level of complexity here. So in order to remember the path, besides the current DP array here, we need another basically the pre-array DP, or you can call it parent. let's call it parents. Okay, the parents here. Uh, so yeah, the parents here. Basically, the parents here, we also have like the two dimension here. So the first one is I, right? And also the second one is also U, I and V here. So this thing represents what? The current, the path of the V here, okay? And when we'll update the parents like nodes here, basically after for each of DPI and J here, right? After we be like traversing the, the all the possible path from U to the current V, we get a minimum, right? And whichever the minimum here, the U here, will be the value inside the parents because we know, okay, so that's our optimal solution here, optimal path, right, from previous one. So basically, every time when we finish updating this, find the minimum for the current DPI and J, we'll remember this U here, and we're gonna update this U to the parent, okay, so that in the end, right, in the end, once we find the minimum value, right, the minimum node, basically the minimum ending nodes from looping through this dpi minus one, this v here, okay, we will have a v here, and then we'll use this v to find to do a loop, and we'll loop back to the parent because we have the ending point. We can use the parent nodes to give us find the parents one layer by one layer up, and we keep doing it until we reach the 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 I0, okay, or sorry, I1, yeah. And then we all we need to do is we just reverse that final result, and then there's gonna be our path. Okay, so I think that's pretty much I want to talk about this one. And yeah, let's try to code these things up. So the code will be a little bit longer, but if you guys understand what we're trying to do here, it shouldn't be that hard to understand. Okay, so like I said, in order to know like which edge, how many edge each one node has, we have to build a graph first. Basically, the way we're building a graph is mm, we're building like the default dictionary here, okay? And then the way we're building a graph is, I'm going to do an am here. We're going to define some of the values here, like for example, the target of path. Okay, that's the am. So here, u and v, right? So in roads, so basically the roads will be our edge, and then the graph dot append u, right? And v, and then graph v dot append u. Okay, so that's the two. That's how we build the graph, and then we're gonna have like a dp here, right? dp. So since we're getting the minimum value, so I'm going to initialize that to a system max value size to so we have n cities, right? So the first element is n cities, and the second one is the I. I is actually the steps basically, right? For in range m plus one. Okay, I'll do m plus one here. And the same thing for the previously one. Right? I'm gonna also define the same thing for the previous. So, but for the previous, I'm going to uh, maybe I'll do a minus one here. It doesn't really matter. I think we can start with minus one or zero for n and the same length basically, right? N plus one. Okay. And now, since the current I means the ith city, right? And I'm let me try to do that. I in range like 1 plus uh m m minus m plus 1. Basically, I'm saying that okay, so the I that's the first city, and sorry, from the first step, right? The first step and to the m step. That's how we continue traversing all the path here. And for each step, okay, for each step, and we will yeah, basically we will loop through all the cities, okay, because at each step we have a way of like we need to loop through try all the cities, okay, and so the second one will be the target, the V, right? The V will be the uh, for in range n, okay, that's all the cities, right? So now we have this DP like I and the V here, right? So how basically now starting here, we just need to get the how many path, right, to the current state. That's what we need when we need to use the graph here. Basically for U in graph, okay, V, right? Basically that's the like how many edges, right, to the current V here. And DP like so and then we'll do a check here. Basically if the DP uh I minus 1 U, right, is smaller than the DP IV, okay, what do we do? We first check this, right? We first do this IV, sorry, uh, we update the I and V, okay, equals to the DP I minus 1 U, okay? And remember, so every time we update this one, we're gonna also update the previously state here. Basically the previously what, oh, so we call it parents. Let's call it parents. So the parents like I and V, right, will become, it's U basically. So by the time the loop is finished, we know we have already find the minimum distance for the current DPI and V, and and at this moment, the uh, the parents IV will also have our path from previously nodes, right? And in the end, we simply need to add. Oh, we haven't finished adding the current cost, right? So what's the current cost? The current cost is one when the names I, right, is not equal to the target path. Sorry, not I. Sorry, the V. Okay, because the current one is V, and the target path is the is is I minus one. Yeah, else zero. So why we're doing I minus one here? Because we are using like a one base, not zero based. Okay, that's why we need to do I minus one to find the current path, the current the expecting uh target, right? Yeah, basically if they're not the same, then we know okay we have one more. We need to add one more added distance. If they're the same, okay, we know there's nothing to be added here. Okay, and yeah, so here actually since we're starting from 1 here, I mean, and we're getting from I minus 1, right? And we need to initialize the I equals to 0 case. So otherwise, I mean, everything inside here will become the is the so all the dp I minus 1 case will start with the system, the maximum one, right? Which will be not correct. Or we can do this from we can put it in 0, and every time we have I and V here, we initialize this thing from the to the max size inside the for loop. Either way is fine, right? I mean, but here let's do for V in range n, right? Basically the dp 0 V will become 0. So this means that if we don't do anything, right? So basically if we don't do any move, the added distance is 0. Okay, right? It's which kind of makes sense, right? I mean, if we don't travel at all, there won't be any added distance. Okay, so after this loop, I mean, we have the data we need in those two arrays. Okay, so now all it's left is to reconstruct the path. Okay, so we're gonna have our answer equals to this, and mm, and we'll have like the minimum distance equals to 6, and the maximum. So the why we're doing the loop here is because not only we will find the actual distance, we also need to reconstruct the path. I mean, if we were only being asked to find the minimum distance, we can simply do this. We can simply return like the dp the minimum of dp I think is n minus 1. Okay, if you only ask to find the minimum distance, we can simply do this because all the values we already saved into in this dp the last dp here, dp n minus 1, and we just need to find the minimum one across all those the ending cities. Okay, I think if we're asking to return the minimum of the distance, I think this one will be more like a medium problem. But here, since we need to reconstruct the path, not only we will need to so we have to remember we need to know which is the ending cities first. So basically, we're gonna do this for v, yeah, in range n, right? Uh, if the dp n minus 1, yeah, if the dp n minus 1 and v, okay, smaller than the minimum distance, okay, right? And then uh, we need a variable here. Yeah, we need to and city. Okay, let's uh, minus 1. Yeah. So and city will be the v here. Okay. Yeah. And in the end, the answer is so we have a first answer. Okay, append and city. Okay. So now, I mean, we have the city here. Okay, we have the city, and then the end city. We know the last one, and now all we need to do is we just need to go back, right? So basically, we need to do it for I in range m plus 1 to 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 1, yeah, because we have already have the end city here, so we just need to loop back m minus 1 times. We start from m plus 1, and then we stop at 2, which make us the m minus 1 steps. So, and basically we're gonna have like the parent. So the parent is like the previous. Uh, actually, it's u, right? U equals to the parent parents I and uh, what's the ending? Okay, so it's gonna be the answers the last one in the answer every time, because every time when we have a u here, we will do an answers dot append u. Okay, right? So now we just use the parents array here. For each of the I here, we use the last element of the current answer, and then we will find the the parents node for a current answer here. And then once we find it, we update the answers so that the next time when we do answers -1, we'll start from here. Okay. Now in the end, we just reverse the answer here. Okay. Yeah, that's basically how this thing works, because we stored the path from the last one to the first one. Okay. Yeah, let's try to run this code. Oops. Uh, oh, I think not when if. Yeah, I use the wrong keyword here. Yeah, I think here it should be m, not m+1, because uh it's zero base, right? So the length is m+1, which means the last element, the index for the last element is m, not m+1. Yeah, yeah, it's m+1. Yeah, and then uh since we already have that we already have the first one. Okay, so that's why we start from 1, not 0. And yeah, it should be m. Run it. Mm. Let, let's see. So let's see. What did we do wrong here? Uh, graph here, and then 2 dps. This should be okay. I think -1 should be okay. -1, then we update 1. Start from each day here, and for each city, okay, we get all the path, right? And here is fine. Get each path, and then we update, and then we add the cost of the current step. And now we're reconstructing the path. We have a minimum distance system and city here. Basically, we're trying to find out the minimum ending cost, right, among all the cities here. Oh, I think yeah. So here, I forgot to update the minimum distance, right? Otherwise, all the cities will be smaller than this, right? Since we need to find the minimum one, I mean, I have to update the distance here whenever we find a smaller one, okay, right? So that we can find the added distance, okay? So yeah, and then end cities, we append the end cities, and from the end city, right, we go back to find the all the parents. Okay, so I think this should work. Yeah. Yeah, even though they have different answers, but this one of this is also the answer here. Okay, submit. What? Hmm. Okay. Again. Oh. What could be wrong? I mean, maybe this one. Let's see. Okay. Let's see. Hmm, this is fine. This is also fine. No, okay, I see. Okay, I know what did I do wrong here. So, I mean, here is dp not n minus 1 because n is the number of cities, but the first one is the length of the path, which is the m. It should be m minus 1. Actually, you know what? Actually, instead of using this n minus 1 or m minus 1, I should have just used minus 1 because this will definitely give me the last element of this dp here, right? So actually, this should be at like n minus 1. Yeah. So, but I was mistakenly used the n minus 1. I believe that's why I failed. Yeah. This one happened. This one succeeded. It happens to be m and n are the same. Okay. That's why I passed this one, but I failed this one because in this one, see the m is greater than the than m, right? The m is 5, the n is n is that. Run it. I think it's m. It's m because we because we define a m plus 1. Okay, so the last one is m. Wow, yeah, finally. Actually, you know what? Yeah, like I said, I should have just used minus 1 here. Just give me the last element. Otherwise, I have to figure out. Okay, oh, I define m plus 1. Then the last element, last index is m. Okay, cool. Run it again. See. Yeah, cool. So this one is passed, right? Just to recap, just I think it's a great DP plus the graph problems. Actually the DP state transition function itself is not that hard, but it just adds like a layer of the graph so to find the different path, different scenario to get to the current state. Okay. And another thing is that once you have that, you also need to maintain like a parent node, a parent array here, so that you can reconstruct the path. Every time when you guys are being asked to print the path, you probably need a second array to keep the path. Every time when you have like a better answer, you just keep updating the parent nodes, so that in the end you can use this one to reconstruct the the path. And Before, I think before finishing these videos, there's like another uh, thing I want to talk about. There's this follow-up question. I'm not sure if you guys noticed this one. Basically, they ask you if each node can be visited only once in the path, what should you change in your solution? You know, currently when we do the for loop here, right? We just loop through everything. Where we let's say this PEK here. We have like we basically will try every possibilities here, 2, 3, and 4. So which means we have visited this several nodes more than once. Okay. But actually this is how this problem was designed, right? And then it asks you, what if the node can only be visited only once? Then now of course the answer will be different, but it's asking you, it try to challenge you, what can you change in your solution, right? So what it means that basically from the for loop here, not every U can be used in our current like calculation here. Let's say for example we 0, 2, 4, 1, right? When we are at 1 here, we cannot go back and we cannot go 2 here. All we can do is we have to go to 3, right? Because both the 2 and 4 have already been used. Okay, so how can we do it, right? I mean, okay, so for this one, I'm not 100% sure, but I'll just throw my thought here. So basically, every time, basically we're gonna maintain like another um, basically we're gonna have like another like current path. Okay, the current path for each of the nodes. Basically the same thing here, right? We're gonna have the current path here, but inside here it's gonna be a set basically. I'm going to create a set inside here, and it's just remember the set for the current set, right? For this for the ending for the current step ending with the cd cd like j here, so that in here basically every time, right, every time when we have like a new number, when we have a smallest number here, we always update this current path with the current I plus the current v, right? How are we going to calculate the set here? Basically we have the u we want to calculate, we want to come from, right? And from this u here, we can find up to u here, what's the user path. In this case, like it's 0 to 4, right? Let's say 0 to 4 saved in this current path from this u. And whenever, because we know where we want to the path coming from u, so that then we can just simply do a append that old set, right? We add the current number, we add the current v here. That's the current cd to the previously set, and then we save it into the current path here, so that every time when we have for u, right? For u in the graph, from the let's see, yeah, so basically, once we have that saved in there, right, we just compare the current V, basically. We check uh, if the V is inside, from the U here, we can find the previously set of the path, right? Basically, we check if the V is inside that path or not, right? I mean, which means if the V is already in that set, then it means that we're revisiting the set the node more than one time. We simply ignore it, right? So for each of the U here, we check if the V is inside that set. If it's not there, okay, then that's fine. Then we can use the current V and we can loop through that U here. Okay. And then in the end, like I said, when we finish find the smallest parent node, and we just update the set, right? The set adding by adding the current V here, and we keep doing it until we just add this check inside in the for loop here, so that we can make sure each path is unique. It's not like revisiting the nodes twice. Yeah. Uh, cool. I think that's it for this problem. Yeah. And yeah, how about the time and space complexity, right? I think the time complexity is this, right? So the first one is m times m times n, right? M times n times so for each n there are gonna be like how many nodes? I think it's also n. Mm, yeah, so this one is like for graph with n total is n. I would say it's also a bounded with n here. Yeah. So m times n squared. That's the time. Space, uh, right? Pretty straightforward. M times n. Okay. And no, maybe we have a set here. I mean, I think the set here is also m times n squared. Yeah, since we have a set here, it's also m times n squared. Yeah. Cool. I think that's it for this problem. Yeah. Very cool problem. Yeah, it's very interesting. It's combined many things into one. Yeah. and you just need to get used to this kind of problem. Yeah, I hope you guys enjoy watching the videos, and yeah, I learned a lot from this problem. Yeah, I hope you the same to for you guys. Okay, thank you so much for watching the videos, guys, and stay tuned. I'll be seeing you guys soon. Bye bye.